Thank you very much. I'm very happy to give a presentation today here in Innsbruck. And some of you I know already more than 40 years. This is a long time. So, and we start with a year, this year, 2022. It's an important year because we have a lot of anniversaries this year. 200 years ago, the German National Academy of Science, the Leopoldina, was founded in Leipzig. And 150 years ago, the Leipzig Meteorological Conference was there, and I gave the spring talk about this conference. And the important thing is, this conference was the preparing conference for the conference in the following year in Vienna, where the International Meteorological Organization was founded, what is now called World Meteorological Organization. And I think the colleagues from Vienna should make a conference too in the next year. And then we have the conference here in Innsbruck. But on the other hand, in 1922, the German Geophysical Society was founded in Leipzig. And 2 years later, 1924, was the second conference of the society in Innsbruck. So we have a lot of connections between Leipzig and Innsbruck, and Leipzig is the town where I have made my PhD. So when I started to prepare this paper here, I was checked the document, which you can see here, is on the digital available, and there was no word atmosphere in the whole document. There was only the word normal atmosphere. Meteorology was not in the document. So why I should speak about turbulence in the atmosphere without atmosphere and meteorology? But I found Reynolds, sorry for the missing S, Reynolds 40 times. I found Taylor 1, Richardson 1, and Wilhelm Schmidt 2 times. So I started my lesson in which of the presentations were these names. And these names were in the presentation of Ekman from Lund. He spoke about streams in the ocean, but and I give you always the original German part and my translation to English. And he spoke about the problem that it's very difficult to determine the friction at the surface. And the problem with the friction was that we have to change the friction coefficient. The friction coefficient depending on the turbulence. And he said there is some progress made by Schmidt, by Taylor, and by Richardson, but the problem was not solved up to now. And this was Ekman. And then I looked which persons I know. And because I'm from Leipzig, so I know, of course, Bjerknes. Wilhelm Bjerknes was the founder of the famous Geophysical Institute in Leipzig in 1913. And he left during the First World War, Leipzig, and built up the famous Bergen School of Meteorology. And also I know Ludwig Prandtl, but both talk about aircrafts. This was also, Giovanni told us the problems which we had after the First World War. And then I looked in the presentation of von Karman, who invited to the conference. And this is quite interesting. He spoke about rotating cylinders and vorticity streets after the cylinder. And this we know in meteorology. We know the Karman's vorticity streets, and here you see a nice picture in the atmosphere of the streets. But I think when we speak about atmospheric turbulence and turbulence in general, we have to go a little bit more back. And for me, the beginning of turbulence is 1895, and this is Reynolds. And in the paper of Reynolds, you see here's the Reynolds number and the Reynolds decomposition. And this is, for me, the beginning of turbulence. And then I show you the next slide, something what you probably didn't know. We are going in Antarctica. The German had an Antarctic expedition in 1911, 1912. And the meteorologist on this expedition was Erich Barkov. And the ship Deutschland, which was after this expedition renamed to Österreich, and the ship Deutschland was there 9 months. It didn't come to Antarctica, it was always in the Weddell Sea. And Barkov had time enough and then analyzed the wind data from the Potsdam Institute, the Potsdam Observatory, where I also started my career. And he wrote that he found some structures in the wind field and called these structures elements of wind turbulence. So the name turbulence element or turbulent eddy comes from this time when we had time in the Antarctica, in the ice, to think about things. And this was done by Erich Barkov. So, and now the question is, of course, two persons, Taylor and Richardson. They didn't were in the conference. Giovanni told us what probably was the reason for this. And I have seen that probably the relationship between Taylor and Brundle was also not the best. Not only because both didn't know the language of the others, and also that Taylor was very much afraid, especially after 1933, about the German policy. But from Taylor, we know, of course, the theory of frozen turbulence. The papers are already written before the Innsbruck conference. And from Taylor, we know something about the turbulence spectra. And I think both things are quite interesting also for atmospheric turbulence. And then we come to Richardson. And Richardson is, for all of us, known as a person who had first made a numerical weather prediction. But he was also very much famous in atmospheric turbulence, but really in atmospheric turbulence. And he has not only given the equation of the Richardson number in a paper 1925, he has also published a nice graph. And this nice graph shows us maybe turbulence depending on the stability in a canopy. And when we look at this graph very carefully, we see the critical Richardson number here, and we see also some gas in this picture. So it's perhaps one of the first pictures where you see current structures and something else in the atmosphere. Yes, and we have seen that in the paper of Ekman, there are 3 names: Richardson, Taylor, and of course, Wilhelm Schmidt. And Wilhelm Schmidt has published a nice book, The Mass Exchange in the Free Air and Other Phenomena and so on. And so it was published in 1925. So for the colleagues in Vienna, 1925, the next conference should be there about this nice work. And from Wilhelm Schmidt comes the word Austauschkoefficient, which is still an English word. And you can use in English language Austauschkoefficient and not exchange coefficient. And what he has written is that the flux depends on something like the Austauschkoefficient and the gradient. And the problem after this work and also after the Innsbruck conference was to determine this Austauschkoefficient and this Austauschkoefficient as a function of turbulence. We go shortly back to Ludwig Brandl, and Ludwig Brandl was asked to write something on the occasion of the 70th birthday of Wilhelm Bergnes, and he said he's glad to write something, but he has nothing in his stock. And so he made something what he could do, and he did a really nice thing. He wrote methodological applications of fluid dynamics or mechanics. And this is unfortunately in German, but it's a nice paper because there's everything what you have to know in micrometrology, for instance, or in fluxes near the ground. And all the equations are in this paper. And this is really the transformation of hydrodynamics to metrology. And you should read this paper, it's really nice. And we have also to go to another person, because I'm from Leipzig, and he was too young to come in the conference in Innsbruck. And he made a PhD in Leipzig, was an assistant in Leipzig of Professor Weidmann, and it's an interesting career. He calculated ballistic winds based on wind profiles and turbulence during the Second World War for the rocket launch from Germany to England. And his role during the D-Day is not really clear. And he didn't talk very much about it, but it is quite interesting, this problem. And he was very shortly after D-Day an American prisoner, was in US during the war, came back to Germany, was in the vessel service, and then go back to US and made the famous O'Neill experiment, wrote the book Exploring the First Mile of the Atmosphere, and was a long time professor of meteorology in the University of Wisconsin-Madison. And he was a directorial member of boundary layer meteorology from the early beginning. So, and now we go back to the conference in Innsbruck, to Wilhelm Schmidt, and we go to two persons, Rossby, well known for you from the Rossby waves, and to Sverdrup, well known for you perhaps from the papers Evaporation from the Ocean. And Rossby wrote a paper together with Montgomery, and I show you a short part of this paper. And he determined the wind gradient and found this part here, and X is a function of the sensible heat. And when you look in this part and say that the height is much larger than the roughness length, then we come to this part, and this part is well known. This is Z over L. This stability parameter Z over L was first published by Rossby and Montgomery. And this paper from Rossby and Montgomery is cited in the papers by Obuchov and Lettau, and both they did know this paper. Interesting is that this was written for isothermal conditions, and Sverdrup made it for the temperature gradient, and the equations from Sverdrup used Albrecht in 1940 and wrote a nice, nearly a book, The Heat Balance of the Earth. It was much earlier than Butico, and the data are not very bad. And this was written with the equations by Sverdrup. Yes, then go ahead. We have Rossby and Sverdrup, then we have Obuchov, the famous paper by Obuchov with the Obuchov length. I must tell you that Obuchow was the first and the only one who isolated the Obuchow length and understood what is the Obuchow length and which role the Obuchow lengths play in atmospheric turbulence. This was Obuchow. But the stability parameter, Z over L, you have seen in Rossby-Montgomery, and you see in Obuchow, and this is here. Sorry, this is not so nice. This is Z over L, and this is a normalized Richardson number, normalized with a critical Richardson number. And the next, the next here, you have to rotate this by 90 degrees in clockwise, and then this is Z over L by Lettau, and then you see the same function, and this is here Richardson number, the same function. So both have weights the same. It's not clear if Lettau did know the work of Obuchow or did not know. I could not find this exactly. So, and after this, then we have the papers by Monin and Obuchow, where they use the Buckingham's p-theorem to explain the Obuchow length and the stability parameter, and they developed the equation for universal functions. And then it was necessary to have the right devices to determine this universal function. And here we had already in the 50s sonic anemometers, but sonic anemometers of the type which we know today, the first was made by Prof. Sheverov in Moscow in 1960, and a little bit later by Kamel. So we have in the beginning of the 60s the sonic anemometers, and then started the measurements to determine the universal function. And one of the first paper was by Sergei Seletinkiewicz and Charlikov of this function, and I think you will talk about this much deeper. And then, of course, we have the famous works by Jos Büssinger and John Wingard. And at the end, I must tell you, of course, a paper by Ulf Högström, who found some errors in the data of the Kansas experiment and determined the right coefficients in the universal function, which we still use up to today, and you perhaps tell us what we have to change in this function later on. So I have no picture from Ulf Högström. I have only one when he is eating lobster, but this is not nice to show you here. So then another problem is the statistical turbulence. So statistical turbulence started perhaps a little bit with Innsbruck. We have the turbulence spectra by Taylor and the famous works about the local isotropy by Kolmogorov. Kolmogorov was a mathematician, and there are additional papers by Obuchow, who has written something about the application of Kolmogorov's theory to the atmosphere. And already mentioned was the role of Heisenberg today. Heisenberg found something else like Kolmogorov in 48, and also Weizsäcker has written a similar paper in 48. The interesting in this time was probably Weizsäcker and Heisenberg didn't know Kolmogorov's work at this moment. And there's a nice story that the English people sent weapons to Russia, and the ships were empty, and then they came back to Great Britain with a lot of Trudi. Trudi are scientific contributions of the Russian scientists. So, and it was Bachelor, and Bachelor made the Russian papers popular in the West. And Bachelor was a PhD student of Taylor, and later on, Obuchov and also Corsin transferred the theory to scalars, and we have the so-called Obuchov-Corsin constant or Obuchov-Corsin parameter. I also want to mention Townsend, who has written some hypotheses like the Reynolds similarity hypothesis, but he has also worked a lot about atmospheric stability, and so it's perhaps an also important person for us. And something is written already in Monin Obuchov similarity theory paper, but I think a very important paper, probably not translated to English, I do not know, is from 1960 from Obuchov, where he determined structure function and turbulence and how to calculate fluxes from structure function and all these things. And this together with the wave propagation theory by Tartarsky was the beginning of remote sensing. And please, Marco Callistrato was one of the first who constructed already in 1960 the first SODA. And I will not go on here which other maybe devices and theories were developed after this, but I think somebody of you will tell us about the new developments in this field. Yes, and coming back to coherent structures and atmospheric stability, and here it's perhaps Stierdorf who has made for the convective conditions some interesting ideas about counter-gradient fluxes in the convective layer, and he has also said that we can solve the problem with higher order closure models, and so it was a beginning of the possibility to investigate this, because we are now at the data available. Of course, we must go back and say, of course, the theories for this were founded much earlier. The Kelvin-Helmholtz instability and the von Wessler frequency were already known at the beginning of before the Innsbruck meeting, but not mentioned in the Innsbruck meeting, of course. Yes, and then I want to say you that Richardson had found coherent structures. They're also in the famous book by Geiger, some measurements made in the 30s of the last century about coherent structures. And I want to remember, of course, Franz Neustadt, who has done a lot in the classification of stable stratification together with Bird, but Bird is here and I have not the picture of Bird. This is my presentation. And then I want to say that Michael Raupach and John Finning have done a lot to understand coherent structures and canopies and made the theories for this. And a lot of people are here who started their work after these fundamental papers. So coming to the end, we have several books about turbulence, starting with Letthaus' first paper, the book from Pasquill, the very important books from Monin and Yarnblom, which were first published in Russian in the 60s, later in English, and still available, and the last edition was made about 15 years ago. Then we have the book by Panofsky and Dutton, also Franz Neustadt wrote a book, and this one, Atmospheric Turbulence and Mesoscale Metrology. The main editor was my friend Evgeny Fedorovich, and we have the nice and fundamental book by John Wingard. The book by Fritschen is, of course, a turbulence, but is mainly connected with Kolmogorov theory. And what I do not know is the end. What is the outcome of this conference? Also a book I do not know. And when you want to go into history of atmospheric turbulence, then you should look at these books of Fritsch. This is from Fyodorovich. And this is a nice book. This is really a nice book. And if somebody is interested, I have it here in the hotel. I can bring it together with me. And also the recurrent structures is important. And in my books are also some remarks about history of micrometrology and history of atmospheric measurements. So thank you very much. And this figures behind here, we had an exhibition in Bayreuth 20 years ago about turbulence art, and turbulence can generate nice figures, and you can see in a museum perhaps, and nobody knows that this is science. Thank you very much.